Good morning, everyone. As the dental ceramics topic is very vast and extensive, I will only be dealing with all ceramic restorative materials and their processing techniques today. You should be writing about these materials if a question on recent advances in ceramics is asked. Tell me honestly, how many of you have felt like this when you were trying to learn about all ceramic restorations? Trust me, even I was like this back in 2011 when I was trying to learn all ceramic materials because this was my LD topic. I was supposed to complete my LD in 3 months, and initial 2 months I was like this. Do you know why this happens? Because we try to identify ceramics by their brand names. This is the biggest mistake. Instead of understanding what class they belong to, we run behind the brand names. I was so frustrated that I was on the verge of quitting and taking up some other topic. That was when I came across this person's exemplary work on dental ceramics. Does anyone of you know who he is? If you don't know, he is Dr. Ed McLaren. I came across this article first and it cleared all my doubts. Later on, I went ahead and read most of his work. What I could not understand in 2 months by reading n number of books and articles, I understood by reading this one article. I always tell my students that the biggest problem nowadays is there is an ocean of information out there, and unfortunately, most of it confuses us. Sometimes we have to be really lucky to find that one author or one researcher, a book, a chapter, or just one paragraph that finally clears the doubt that has been pestering us day and night. I think we should never stop searching for that moment of clarity, because when we do find it, it doesn't just answer our question, it heals something from within. You must be wondering what was so special in that McLaren's article. The speciality of that article is it aims to clarify many types of ceramic systems by organizing them via microstructural features and processing techniques rather than just by commercial brands. This is powerful because many of key mechanical, optical, and aging behaviors of ceramics are strongly tied to their microstructure. So following McLaren, I'll be walking you through different types of all ceramic systems based on their microstructure. Let us first go ahead and understand what is microstructure. All ceramic materials contain two key phases, and they are the glassy phase and crystalline phase. And all these materials belong to one of these categories. Some may be predominantly glassy, some may be predominantly crystalline, and some may have both. In short, the arrangement of these glassy and crystalline phases as well as their proportion is what we call as microstructure. The amount of glass and the amount of crystal inside a ceramic decide everything, like how strong it is, how translucent it looks, how it bonds to the tooth, and even how it is going to fail. And let me give you an example. A ceramic that is mostly glassy will look very beautiful and highly translucent, which is perfect for veneers where aesthetics is priority, but that same material when put under heavy masticatory forces will crack. On the other hand, when the crystalline phase dominates, the material will become obviously stronger and resistant to fracture, but the aesthetics will be compromised. Now that we have understood the microstructure, in the next part, let us walk through the family tree of ceramics from the most glassy and aesthetic to the toughest and strongest, and see how each one of them evolved from the other. Recently, different authors have numbered these categories a bit differently, yet the fundamental families remain unchanged. So you should not get confused about these. Let us explore each one of these families and see what they are made up of, how they are processed, and where they are used. First, we will consider predominantly glass-based systems. We will now see what is it made up of. The main ingredient it has is feldspar, a mineral whose optical properties are similar to the tooth. In addition, it has quartz as well as kaolin as a binder. When all of the above ingredients along with the coloring fluids were sintered together, aluminoborosilicate glass was obtained, which exhibited excellent optical properties but was very fragile. As the name suggests, The microstructure of predominantly glass-based ceramic mostly is made up of glass with only a small amount of crystalline content. As could be anticipated, the extensively glassy structure made this material prone to fracture and hence could not be used alone to fabricate indirect restorations. If it is not used for fabricating the restoration, can you guess where it is used? What do you think this is? Exactly. It is used as add-on glaze. Let's see what was the next step in the research. Researchers were extremely happy with the aesthetics of predominantly glass-based ceramics, but unfortunately, we all know that it was too brittle and could not be used as it is. Then they thought, why not layer it over a strong metal base? A true win-win, isn't it? By this, they felt aesthetics and strength could be achieved in one single restoration. So, what do you all think? Did the porcelain layering on metal really work? No, sadly it didn't. Let me explain. When they attempted to layer the ceramic on a metal substructure and then try to sinter it, the ceramic started cracking during cooling. This happened because the metal exhibited a very high coefficient of thermal expansion or CTE compared to the porcelain. Therefore, as you can see in this video, the metal pulled away on cooling after sintering and the brittle porcelain fractured. There was a simple solution to this problem, and that was to closely match the coefficient of thermal expansion of metal and ceramic. There were three ways to accomplish this, either by decreasing the coefficient of thermal expansion of metal or increasing the coefficient of thermal expansion of porcelain or a combination of both these adjustments. And they chose both of these options. The coefficient of thermal expansion of metal was reduced by the addition of platinum and palladium, whereas the coefficient of thermal expansion of porcelain was increased with the addition of lucite crystals. One more reason for choosing lucite crystals was the refractive index of it is similar to the glassy matrix, and when the light falls on it will not be scattered. Hence the aesthetics will not be hampered. Interestingly, it was also noted that addition of lucite crystals had increased the flexural strength as well as fracture toughness of the porcelain. Though it was not primarily intended, it was a good news. In essence, lucite crystals had three main functions: to raise the coefficient of thermal expansion of ceramic so it matched the metal, to strengthen the material mechanically, and to enhance its optical properties. Porcelain thus modified is called as feldspathic porcelain. In short, it is nothing but predominantly glass-based ceramic plus mechanically added lucite. If you are wondering, after these modifications, could they successfully layer this material on the metal core? The answer is yes. This gave way to the next big leap, the metal ceramic restorations, which brought together the strength of the metal and beauty of porcelain. Now, can you tell me which category it belonged to? Without any doubt or without any confusion, we can say that it belongs to category number 2, that is glass-based systems with fillers. Because the glassy matrix was obtained directly from predominantly glass-based systems and the fillers added were lucite crystals. So we have a combination of both of these. Initially, feldspathic porcelain was available in powder liquid form and was used to layer metal substructure to fabricate metal ceramic restorations. Later on, with the introduction of other all ceramic restorations, it was modified to layer them as well. In this slide, you can see different varieties of layering porcelains. My question to you is, can we just take any random material and layer it on any random substructure? The answer is a strict no. You should be able to reason it out now. It's pretty simple because every core material has its own coefficient of thermal expansion. The lucite crystals in porcelain need to be adjusted according to it. Hence, veneering materials cannot be swapped. They are formulated specifically for a specific core. After a decade or so, with the technological advances, convenient machinable blocks were introduced. These machinable blocks are basically used for fabricating veneers in low stress bearing areas. A word of caution here: feldspathic porcelains still contain a large glassy matrix and are considered brittle. Placing the veneer entirely on dentine could be problematic because dentine has low modulus of elasticity and it is going to flex. That can easily crack the brittle porcelain veneer. You can simply go ahead with these veneers when the preparation has more than 50% enamel. Because of the larger glassy content, feldspathic porcelains are still weak and have limited clinical use. Therefore, to overcome the weakness of feldspathic porcelain, researchers try to modify its composition. We have already seen at this stage aesthetics was not at all a concern, but strength was. And by now they had realized that adding crystals will enhance the mechanical properties. So using this idea, aluminous porcelain was developed. It was called as aluminous porcelain because alumina particles were added in feldspathic porcelain. As presumed, the alumina crystals were able to reinforce the feldspathic porcelain, making it more resistant to fracture by crack shielding mechanism. As promised earlier, I will explain you about crack shielding mechanism now. Usually, porcelains fracture by the formation of crack and its propagation through the object. With the addition of around 50% alumina crystals, which were extremely hard, something interesting happened. Any crack trying to pass through the glassy matrix would hit a crystal, unable to pass through it would divert around it and then encounter another crystal. This process effectively slowed or even stopped the crack propagation, thus significantly improved the porcelain's strength. Have you heard about porcelain jacket crowns or PJCs? They were the first all ceramic crowns made primarily from aluminous porcelain. These crowns were fabricated by adapting a platinum foil on the die and then layering aluminous porcelain over it, followed by its sintering. Here also there was a problem. Though aluminous porcelain was stronger than the feldspathic porcelain, it was more opaque. This was because of the presence of alumina crystals, which are very opaque. Moreover, the strength was also still not enough for heavy masticatory forces. Therefore, the aluminous porcelain never fully replaced feldspathic porcelain, though it improved the strength, but it was at the cost of aesthetics and long-term reliability. The researchers again turned their attention back to the lucite for its aesthetic benefits that alumina crystals simply could not deliver. Then they realized that the low strength of feldspathic porcelain was due to low lucite crystal content, which was just 35%. You must be thinking, now we know higher the crystal content, higher is the strength. So what is the big deal? Come on, bring in more crystals. It was not that easy as it looks. But why? Why was it not possible? Adding more crystals was not possible because of the method of their incorporation. So, what was that method? The lucite crystals were mechanically added to the molten glass during manufacturing. Little difficult to understand, isn't it? Okay, in simple words, it's just like mixing your coffee powder in the milk and stirring it. So what was wrong with this method? When they tried to load too many lucite crystals into the glassy matrix, the crystals started clumping together. They disrupted the glassy phase continuity and the porcelain lost its workability and translucency. Okay, in Gen Z words, everything was getting messed up. The next step was obvious. Change the incorporation strategy. Simple, isn't it? Researchers adopted controlled crystallization or ceramic technique where the crystals nucleate and grow within the glass. Okay, in simple words, lucite crystals were not added from outside. Instead, they were grown within the glassy matrix and hence they were called as homegrown crystals. Nice name, isn't it? This approach produced a more uniform distribution of the lucite crystals and allowed a higher crystal volume fractions of about 50%. By this method, they increase the crystal content from 35% to 50%, and here are the results. Feldspathic porcelain showed flexural strength of 60 to 70 MPa, while lucite glazed glass ceramic showed a flexural strength of 120 MPa. This was almost doubled up. When they successfully started home growing the lucite crystals, they realized just by tweaking a little in composition and nucleating agents, other crystals like lithium disilicate and fluoromica crystals can also be grown in the glassy matrix. Like this, a total of 3 groups of ceramics were added in this category. These ceramics are called as glass-based ceramics, and the 3 categories under this group are lucite-based, lithium disilicate-based, and mica-based glass-based ceramics. Lucite-based and lithium disilicate-based ceramics are currently widely used, whereas mica-based ceramics, which were originally known as dichroic crowns, are not much in use. These ceramics are also known as castable ceramics because they are processed by casting technique. Lucite-based and lithium disilicate-based ceramics are processed by two main techniques, and they are heat pressing technique and CAD-CAM milling. Let us see how these ceramics are processed by heat pressing technique. Wax patterns will be applied on the ring gauge. Investment material will be mixed using a mechanical mixing device. Usually, phosphate bonded investment material is used. The investment material will be painted on the wax pattern to avoid voids. Then the silicone ring will be placed on the ring gauge. Investment material will be carefully poured inside the ring and it will be allowed to set. After it completely sets, the set investment is removed and it is placed inside the wax burnout furnace. After the wax burnout, we will have empty mold space into which first the ceramic ingot is placed and then the external alumina plunger. The entire assembly will be placed in heat pressing machine, which is going to press the molten ceramic into the mold space. After the investment cools down, devestment will be done by sandblasting. Final finishing and polishing of the restoration will be done. If needed, external stains will be applied and then add on glaze and then it will be sintered. Let us see what are the heat pressable material options available to us. Pressable lucite based glass ceramics are sold as M-Press ingots. I'm talking about the brand here because you all will relate to it, as these are routinely used by Indian dental labs and there is a lot of confusion regarding M-Press and E-Max. Pressable lithium disilicate ceramics are sold as E-Max press. So M-Press will have lucite crystals and E-Max press will have lithium disilicate crystals. Let us see how the CAD-CAM milling of glass-based ceramics is done and what are the material options available to us. Discussion about all ceramic restorations is incomplete if we don't talk about monolithic restorations. Monolithic restorations will be made up of just one material and there will not be layering of porcelain done. Let us compare a monolithic and layered ceramic restorations. The first image shows a layered zirconia restoration where a stronger core having a flexural strength of around 1000 MPa is layered by porcelain having a flexural strength of just 90 MPa. With this, literally the final strength of the restoration gets reduced to around 90 MPa. Usually, the failures occur in these restorations by either delamination or fracture or chipping of the porcelain. On the contrary, if you compare it with lithium disilicate monolithic crown, though it is not as strong as zirconia, it still holds an ultimate strength of around 400 MPa. That's way higher than the mere 90 MPa seen in the veneering porcelain of layered zirconia restorations. So even though lithium disilicate is technically weaker, the monolithic version of it performs far better clinically because there is no fragile veneer waiting to chip off. When compared to lithium disilicate, lucite based glass ceramics have half the flexural strength but better aesthetic properties. That's why they are used for fabricating anterior crowns, veneers and inlay. Whereas lithium disilicate crowns are advocated for anterior as well as posterior crowns, veneers and inlays, onlays and anterior 3-unit bridges, but not posterior bridges. Though the strength of glass-based ceramics was improved compared to the earlier ceramics, it was still limited because of the inherent weakness of glass matrix. Then the researchers thought, let us do exactly opposite of what we have been doing. This gave birth to an entirely different subset of ceramics which belong to category number 3. Instead of having glassy matrix, these ceramics had crystalline matrix and glass was used as a filler. In simple words, all this while we saw ceramics which had glassy matrix and crystals as fillers. In the next system of ceramics, we are going to see crystalline matrix and glass as fillers, exactly opposite of what we had earlier. You will all understand what it means to have a crystalline matrix with the glass as filler when we get to the slip casting technique. The materials hence developed were called as glass infiltrated ceramics. There are again 3 categories in glass infiltrated ceramics and they are in ceram spinel, in ceram alumina and in ceram zirconia. These ceramics are processed by 2 techniques, slip casting and CAD/CAM milling. We will now see what is slip casting technique. In the first step, an impression of the die is made with an elastomeric impression material. A highly porous and refractory gypsum dye material is poured into the impression and the duplicate dyes are obtained. Alumina powder is mixed with deionized water and also 1 drop of a dispersing agent is added to help create a homogeneous mixture of alumina in water and the resultant mixture is vibrated in ultrasonic machine. The sonicated material is nothing but a solution of alumina and that is called slip. And that slip is applied with the help of a brush on the die. When the slip is applied to the die, the excess water will be pulled inside by the capillary action of the porous gypsum, which is going to pack the particles into a rigid network. It is then sintered in the sintering furnace and during sintering, the water and the binding agent will be removed. Thus an interconnected porous network is created, connecting pores on the outer surface with those on the inner surface. As we discussed before, this is how a crystalline matrix will be formed. Lanthanum aluminosilicate glass powder of appropriate shade is mixed with distilled water and applied over the external surface of sintered substructure using a brush. It is then placed in the furnace and fired. During firing, the glass becomes molten and flows into the interconnected pores by capillary diffusion. In other words, the glass gets infiltrated into those pores. That's why the name glass infiltrated ceramics. The excess glass is then removed with a coarse grain diamond instrument almost down to the substructure surface. The residual glass is sandblasted in a sandblasting unit. The last step in the fabrication of the restoration involves the application of aluminous porcelain to the core to produce the final form of the restoration. I could fortunately find a real life in-ceram CAD milling video, which is very rare. Let's watch it. A machinable in-ceram alumina block is being milled in a CAM machine. The block is attached to the machine. The wet milling has started now. A coping has been milled. It's being tried on the die. Finer adjustments are being done. It's being sintered in the sintering machine. Again tried on the die. Crack disclosing dye has been applied. This will disclose if there are any cracks found on the surface. Now lanthanum glass is being mixed with distilled water. With the help of a brush, it is layered. It is going to be sintered in the sintering machine. You can now see the glass is infiltrated. Excess of the glass is being trimmed. It's being trimmed to the core or the substructure. It is then sandblasted using 50 microns alumina particles. A final sintering is done. So the core is now ready for final buildup. In-cera materials are approximately 2 to 3 times stronger than earlier generations of ceramics. The enhanced strength is obviously credited to their predominantly crystalline microstructure with only minimal glassy phase. To cause ultimate fracture, the crack would have to fight its way through a tough crystalline framework with a very high modulus of elasticity. If we look at all three glass infiltrated ceramics in the InCeram family, there is a very interesting pattern. When it comes to strength, InCeram zirconia tops the list and it has the highest structural strength. At the other end, InCeram spinel shows the lowest strength, while InCeram alumina sits somewhere in between. On the contrary, when we talk about aesthetics, the trend flips completely. Spinel is the most translucent and therefore more aesthetic. Zirconia is the least, and alumina falls right in the middle. So it's always a trade off. The stronger the material, the less translucent it tends to be. And that's a balance we constantly juggle in restorative dentistry. Because in ceram, spinel is more translucent and it is weaker, it is only limited to anterior crowns and inlay. In ceram, alumina is slightly stronger but less translucent than the spinal cores. Thus, they are recommended for anterior and posterior crowns and anterior fixed partial denture. As in ceram zirconia is strongest and least aesthetic of all, it is indicated for posterior crown and bridge applications. Even though in-ceram zirconia possessed flexural strength enough to fabricate 3-unit posterior FPD, a long span bridge was still not possible because it had glassy phase in it. Though less, but it did have a glassy phase. To eliminate any of the glassy phase, the last category of materials was introduced, and that is polycrystalline ceramics. There are two subcategories of materials in this, and they are zirconia and alumina. These materials do not have any glassy component, they are completely crystalline. Of the two varieties, zirconia and alumina, zirconia is very important because that's what we are using in day-to-day practice. Zirconia is often called as ceramic steel of dentistry because of its remarkable combination of strength, toughness, and biocompatibility. Unlike traditional brittle ceramics, zirconia has a unique ability known as transformation toughening. Let us learn about transformation, strengthening, or toughening. Zirconia exists mainly in three crystal phases like tetragonal, monoclinic, and cubic. At room temperature, it exists as monoclinic phase, but when it is heated to 1170 degrees centigrade, it gets converted into tetragonal phase. You can very well appreciate in this figure that monoclinic phase is larger and it occupies about 4.4% more volume than tetragonal phase. By adding 3 to 8 mass percent yttrium oxide or cerium, it is possible to retain the tetragonal phase at room temperature. Although stabilized at room temperature, the tetragonal form is metastable, which means trapped energy exists within the material to drive it back again to the monoclinic state. Please watch this figure carefully. It shows the specimen of zirconia, and these are tetragonal crystals stabilized at room temperature. Hypothetically, think that a crack forms and starts propagating. There will be highly localized stress concentration at the crack tip, and this stress will be sufficient to trigger grains of ceramic to transform from tetragonal to monoclinic, that is T to M transformation. This occurs in the vicinity of the crack tip. As we already know, monoclinic zirconia occupies 4.4% more volume than tetragonal form, so the crack will be closed instead of propagating further. So this phenomenon is going to give zirconia an exceptionally high flexural strength, often exceeding 1000 MPa, making it ideal for posterior crowns, bridges, and implant abutments where mechanical demands are highest. There is only one technique available for fabricating zirconia restorations, and that is CAD/CAM milling. I think I have to stop here because I have already crossed my presentation time. Just a quick recap before I sign off. As you can see here, feldspathic porcelain has a flexural strength of only 60 to 70 MPa. So it is used as layering material and to fabricate veneers in low stress bearing area. As far as possible, avoid layering the porcelain over a stronger core and instead use monolithic option, as the final strength and longevity of that restoration will be decided by the layering porcelain, not by the core. Coming to lucite based glass ceramics, they have a flexural strength of around 120 MPa. Though double than that of feldspathic porcelain, it is still not that great. Therefore, it should be used for anterior crowns and veneers only when the aesthetic demands are very high. Lithium disilicate based ceramics have a flexural strength of 360 MPa, which is quite acceptable for anterior restorations and even 3-unit anterior bridges. Though it is claimed after bonding their fracture toughness improves, you need to use them with caution in the posterior region of the mouth. The glass infiltrated ceramics have a balanced aesthetics and strength, and you can choose the subsets from this family accordingly. Zirconia ceramics having a flexural strength of over 1000 MPa are on the top in the list when it comes to strength, so are best suited for posterior region. As discussed earlier, as far as possible, try using monolithic restorations over layered options. The layered zirconia has been tried successfully for anterior restorations as well, but they are not as aesthetic as lithium disilicate ceramics, and moreover, they cannot be bonded. Recent translucent varieties of zirconia are already there in the market, but they are not as strong as TZB zirconias.